All right, welcome back, everybody. Hope you all had a good weekend. Let's kick some ass on chapter 6 today. Chapter 6 in math 21 is on discrete probability distributions. Discrete data. All right, so recall, discrete data. We talked about this in chapter 1. Discrete data was countable data. Whether you wanted to count it or not. You could, it uses numbers like 0, 1, 2, 3, etc. That's chapter 6. Chapter 7 is on continuous data and probability distributions through that. And that's data that you gathered by measurement. Whether you use a stopwatch for time or some sort of ruler equivalent for length or a scale for weight, something you'd measure. So some things you're going to want to know for chapter 6, 6.1, first section we're doing is on discrete random variables, what they are in general. Things that you're going to need for this are expected value. We're going to cover this all, but I'm just giving you a nice summary at the beginning. It goes by E of X like that. And it's the summation of X times the probability of X. And this is actually the same as the mean. So this will be our mu. Or mu of X data. The other thing you're going to want to know is stat crunch takeaway. Stat crunch, we will use, it's under stats, calculators, custom. All right, so it said that this section's on discrete random variable. What's a random variable? A random variable. And we say this a lot from here on. I'm going to abbreviate RV because you're going to get tired of writing random variable. But if you get used to calling it RV, you can save yourself some time and effort. Random variables are numerical measures of the outcome. Probability experiment. We use a capital X or a large X to describe the category of the outcomes. And the lowercase x. And this is for individual outcomes. All possible numerical outcomes. Let's say Inmar and I play rock, paper, scissors. And we record the number of times Inmar wins. And let's say wins out of 5 games. So the category, the big X, capital X, is going to be number of wins for Inmar. And little x, the possible outcomes, he could win none of them, he could win one of them, 2, 3, 4, or he could crush my soul and spirit and win all 5. So we go with, what is the probability? That Inmar wins exactly 3 games. And what about 3 or more games? So we would write this as probability that big X equals 3. And we would write this as probably that big X is greater than or equal to 3. We tend to write this as probably big X equals the small value. So it tells us what the category is. And it tells us our target number. And we can have any of the inequality symbols in here. This could be equals, this could be less than or greater than, could be less than or equal to or greater than or equal to. And because little x has finite or limited countable numbers. This falls under discrete data. Did anyone watch Survivor? Did you watch like the start of this new season?
No, I haven't started this new season.
So one of the guys in there started talking about the math of being selected, and he did an N choose R. And he's doing with his finger in the air, and then they like fucking Survivor put like the numbers and the equation up on there. And I said, I'm gonna bring this up, tell my students about it. He was like, there's like, I don't know, 15 people in the groups, and it was. The probability of getting chosen for something, he was talking about it. I liked the guy in the beginning, and he ended up, I think he was the same guy that I didn't like at the end. But he didn't get voted out, which let me down. I think it was the same guy. You'll see. Apparently the new one started, there's only been one episode, I didn't know. Okay, so. Things we have in here are, in this today, are gonna be probability distributions. We're gonna be doing this in all of these stuff. So we need to talk about what a probability distribution is. It's a table listing all possible outcomes. And their respective probabilities. We weren't gonna calculate the number of times Mar wins, there's too many variables in it. Like how well he can read me and stuff like that, but it did show. What the idea is here for what a random variable is and. Numerical measures of outcomes. Okay, so. Some of the requirements for, or two of the two major requirements. For probability distribution. Each individual probability. Probability that big X equals little x has to be between 0 and 1. I think we've talked about this before, probabilities have to be between 0 and 1. And the sum of all probabilities. Has to equal 1. So let's take a look at an example. And this is an old example, so the numbers have probably changed. So the number of movies streamed from Netflix. In a single month. Pre-pandemic. When the world fucking changed and actually streamed entertainment, it got so much more popular and we never let it go. So big X will be, the category is number of movies streamed. And we're gonna make a table of the number. So 0, 1, 2, 3, 4, and 5. And probabilities associated with those values. Probability that X equals 0 was 0.06. Probability that X equals 1 is 0.58. Probability that X equals 2 was 0.22. Probability that X equals 3 was 0.10. Probability that X equals 4 was 0.03. Probability X equals 5 was 0.01. So we don't have individual data here. It's just summarized data. That affects how we tackle it. What we're dealing with today is how we tackle it when we don't have the individual data. First off, let's verify that this is a probability distribution. Where's Bianca and her way out? I didn't want to write that first there. I wanted to write something there a little bit. Oh, well. Actually, that line's easy to write. Never mind. So first question, are all probabilities between 0 and 1? I don't see any negative signs and the number in front of the decimal is 0 on all of them. So yes, this criteria is met. Second thing we gotta check is the sum of the probabilities 1? this, I'll add them up. 6 and 8 is 14. Plus 2 more is 16, plus 3 is 19, plus 1 is 20. Carry the 2. 2 plus 5 is 7, 7 plus 2 is 9, 9 plus 1 is 10. And there's nothing over there, so we do that, and the decimal point was there. So yeah, it did add up to 1. So we do have a probability distribution. Now, we saw in like chapter 3, we like having the mean for a lot of stuff. The mean tells us where the center of the graph is. The mean is a nice summary. Phenomenally easy to get if we have the data. We just compute it normally. Compute it normally. And if it was in StatCrunch, we would do. Was it stats? Columns. I think I'm doing that right. Stick back to chapter 3 and look at that. I know what I'm looking at, but I'm not looking at it right now. Nope, stats, summary stats, then columns. And we choose our column and we choose the mean. We've done this. We don't have that here, so we can find the mean of summarized distribute or summary. The mean of the summary will be, we're gonna take x, multiply by p of x and add that up. So I'll do that up here on this table. I'm gonna make an x times p of x column. And I'll start at the bottom where the numbers actually have something to multiply. We take the 5 and we multiply it by the 0.01. That 5 and that 0.01, and we get 0.05. I'll take this 4 and multiply it by its probability, 0.03, and I'll get 0.12. Take this 3 and multiply by that one, 0.30. Two times 0.22 is 0.44. And I can do the last two quickly. What's 1 times any value? It's just a value. What's 0 times a value? Just 0. And maybe I'll put 0.00, that way I have 2 decimal places and everything. If I add up all of these numbers, and I probably would do it in a calculator. Mu of x should equal 1.49. So that's the average number of movies streamed in a month. Now, if Netflix gave us the actual data, each person's each household, how many movies they watched. We just start a StatCrunch to do the stats, summary stats columns and be done with it. To do this in StatCrunch. Stats, calculators, custom. And the table needs to be already entered. And StatCrunch to do this. No, it's not possible to watch 1.4. It doesn't make sense to say I watch 1.49 movies. Usually the mean is not one of the outcomes. It's an average, so very rarely is an average, it's an actual number. No one's watched 1.49 movies. That would take some phenomenal measurement to say I watched 0.49 of a movie. So that the mean doesn't actually happen. We have discrete numbers of movies we watch. But it's an average. And it's more of what we expect to happen in the long run. The mean value of a random variable. Or mu of x. As I was saying, it is what we expect to happen in the long run. And thus, we call it expected value. And we're gonna tie this back into the little piggies thing we did a little bit earlier. If we had the data. The mean would be X bar. We do the average that way. The mean X bar is approaching mu of X. The population outcome or population mean. Whereas X bar was a sample mean. As n gets larger, the number of people we survey. And eventually. X bar is close enough to mu of X to use it. By the law of large numbers. It's called the law of large numbers. Remember, we looked at what would happen if we added one more. Pig and tried to get a leaning jowler, and it didn't change the probabilities at all. At some point, making n larger doesn't really change anything. Or not enough to be important. Finally, let's talk about some fun. Let's talk about roulette. There's two forms. European. Has numbers 1 through 36 and then a single zero. And the American version. Has 1 through 36 and then 0 and double zero. Of these, the 1 through 36. Half are black. Half are red. And it's not in order, it's not like the first 18 are black and the second 18 are red. I'll show you images of both tables in a second. You've never seen roulette, you've probably seen it even if just in a movie. You've never been to a casino, you've probably seen it in a movie. It's the one where there's a wheel spinning and they flick a marble on it. You guys ready to go look at the roulette table? Here, everyone's ready. Operator's still right now. I want to rush me. You good? Okay. You can change this one as well. So to spin the table spins at a constant rate. And they flip the marble the opposite direction. So that eventually friction makes the marble wear down, slow down, and eventually falls in one of these. There's little buckets right here. On the inside. I see that better. So the single European one has a single aught, it's called, or single zero. The colors are broken down as thus. You can bet on lots of things. You can bet on whether it's red, whether it's black, whether it's in the first 12 numbers, the second 12 numbers, the third 12 numbers. You can bet if it falls in this column or this row, this row, this row. You can bet on the first half or the second half. You can bet on odd or even. You can bet on any single number by putting your chips on the number. You can bet on two numbers by putting your chips on the line between them. You can bet on four numbers by putting it, like if you put it in the intersection of 1, 2, 4, 5. You're betting on all four numbers, it's just a reduced payout. There is a way to bet on three numbers, but it's only up here with the zero. You have to bet on, like, you could do 0, 1, and 2 by putting your token or your chip right here. And this is something, I had never seen this one, it's a sequence bet, like betting on a certain range of numbers. The American table looks very similar, except it's got two zeros. 0 and double zero. This one doesn't have the same thing going on. They've got a track here where you can bet a range kind of thing. I haven't actually seen this in a casino, but they're showing it. Up here, they got more stuff. I never even read, I just read about Ophidians and shit like that today. That's kind of neat, but we're gonna go look at computing this shit. What's the probability of something happening? What the hell is that? Share events screen. So let's look at the probability of winning on a single number. We're gonna play the American version. Let's bet on. Gilda, what's your favorite number? And don't pick a number over 36. 7. 7? Let's bet on 7. Lucky 7. So when you bet on a single number. The payout is 35-1. 35-1. And you might see it listed as 35-1. They usually don't have the 2 in there, they don't have the $sign in there. In fact, if you saw on the table, some of it, at one point it said 2-1 for like the rows and stuff. So let's develop a probability distribution for this. So we'll have an outcome. What type of outcomes can we have for this? We either hit the 7, the ball hits the 7. Or the ball misses. And if we're gonna do a probability distribution on this, we need to have some numerical thing associated with this. Let's relate this to our winnings. So my X here, if the ball hits the 7, for every dollar I spend, I win $35. And if the ball misses the 7, I lose $1. Right? What's the probability of this happening? Well, there's only one spot on the wheel that has a 7. How many total spots is there? There's 38. 36 plus the 0 and the double 0 add up to 38. So the probability of us winning is 1/38. And that means the probability of us losing is 37/38. Every other number is a losing number. Now we can see right away, if we add these up, this adds up to 38/38, which equals 1. This is going to be a probability distribution, it's gonna work. But if we wanna calculate our expected winnings. Per dollar bet. We need to do X times P of X. So maybe writing these as a decimal will be more helpful than a fraction. 1/38 is 0.0263. And 37/38 is approximately 0.9737. So to find my expected winnings, I'm gonna do X times P of X. So 35 times 0.0263 is 92 cents. And -1 times 0.9737 is to 2 decimal places, -97 cents. So if I add those up, my mu of x or expected winnings. Is negative 0.05. In the long run, you lose a nickel for every dollar bet. You will. It's not a question. You will lose a nickel for every dollar bet. Or wagered. They like to call it the wager. Now, short term, you might do pretty good. Like $35 doesn't sound like a lot, but that's only betting $1. If you drop to 10, all of a sudden you just won 350 if that 7 hits. That sounded pretty good. People like roulette because it's easy. And you can win big, it just doesn't happen a lot. Other things like we saw on the other table, they had a spot for red or black, odd or even. Those are all odd or even pay 1-to-1. Like the rose paid 2-to-1. The interesting thing about roulette, no matter the wager. Expected value is negative a nickel. Doesn't matter what you bet on, you can work out this probability distribution. Doing odd or even. It's related to the 0 and double 0 are green, so like. They don't affect the red or black, they're not part of numbers, they're not considered odd or even. They're outside the system and they give the house an advantage. If you're lucky enough to see, and you play roulette. If you're lucky enough to see a single wheel table or a single 0 table. It drops down to like 2.7%. Or 2.7 cents. About half. So the house edge. Or the amount that house is gonna take home in the long run is less. You have a better chance of walking away with something. It's still below half. But you have a better chance of walking away with something if you see a single 0 table. Oftentimes in America's casinos like Vegas and stuff, the single 0 tables are usually the high money tables. And if you're gonna play there, they make you like. Use the big chips, not these dollar chips shit. I don't wanna hear about your dollar with the single 0 table. Let's look at another type of problem you'll see in this category. We might need that a longer. Alright. One of your home problems, I'm sure, is still in the system like this. It's on term life insurance. So let's say a lady pays. $530 annually for life insurance. Life insurance coverage for the next year. Insurance companies don't allow you to do anything but prepay for that shit. They are like, fuck you. If you die, we can't collect, so you gotta pay ahead of time. The policy is worth $250,000. And the probability of a woman her age surviving. With her health factors and shit like that. Is probability of survival is 0.99791. Or 99.791%. Highly likely to survive. Let's compute the expected value. For a life insurance company. So I'm gonna make a column for what the outcome is. Then we will put a numerical value associated with it. Probability of that associated with that. What are the two outcomes of a life insurance policy?
Life or death?
Life or death, simple as that. Now, from the company's perspective, if she lives, what happens? They get the money, they don't have to pay anything. Pure profit, $530. And we said the probability of survival was 0.99791. That was given to us. If she dies, how much does it cost them? Close. They are gonna have to pay $250,000
Is it minus the 530?
minus the 530 that they already collected. You go. Check that out. Clever girl right there. $250,000 paid out. But they already collected $530, so they get to keep that shit. So that is negative. We're gonna treat it as a negative. Cause it's a lost money, negative $249,470. What's the probability of death? The fucking dark thing to ask,
Why did they keep the 530?
cause she already paid.
They're paying 250.
They're paying $250.
If I paid 530 in January and I die in February, my family should get 250 because I paid up front. I didn't get those 530.
They get $250. They get the full $250. Yeah, the family gets the full $250. But from the company's perspective. They didn't actually lose $250,000 because they've already collected $530 of that. So they will pay out $250,000. But the actual loss is that. That's an excellent, no one has ever asked that. That's a great question. You already paid it,
My money.
it's your money, your family gets the full dose. What's the probability of death?
0.00209.
Shit, you wanna teach this shit, how'd you get that?
I have a calculator.
That's, of course you gotta calculate, how'd you get it though? That's not just, the calculator doesn't just give you that.
Well, because it's supposed to equal 1, and so if that's 99791, 0.99791, you just subtract that from 1.
Excellent. I wanna make sure everyone understands that, cause it's not gonna tell you that. We know the probability of life is 0.99791. But we don't know the probability of, skull and crossbones. So we can find it by subtracting. 1 minus 0.99791 gives you 0.00209. So if we do an x times p of x column, If you multiply these two values, you should get $528.89 for that one. And negative $521.39 for this one. For a net total of $7.50. In the long run, they can expect to gain $7.50 per policy. That's the kicker. Assuming it's the same thing for every woman in that same state circumstance. And I imagine they do the life insurance policies all set up something like this. That doesn't seem like a lot, but. Think about how big some of these life insurance companies are. They have millions of people. Even if you only had 100,000 people. $7.50 times 100,000 people. I just moved the 1, 2, 3, 4, 5. 5 zeros, that's 750,000. That's almost $1 million for 100,000 people. Make it 1 million people, and now you're talking almost 10 million, 7.5 million. So it's not much gain on each policy, and some policies they have to pay out. And some policies, most policies, they just collect the money. But they collect enough money on the $530 to cover the losses on death, paying the $250. Pay the $250. That they make a good chunk of change in the long run. Let's go look at this in StatCrunch real quick. As a reminder. We're gonna do stats, calculators. Custom. It's gonna ask you for two things. Values is where we're gonna put our X outcomes. And weights is where we're gonna put our P of X. And while you're writing that down, I am gonna go load StatCrunch. And then we'll take a break. This won't take that long though. All right, assuming you're with me. Going to StatCrunch. Visit the website. So I'm gonna call this X. And P of X. That way I already know where to look. And we had 530. And negative 249. 470. And I had 0.99, that's not 99, that's 791. And here we had 0.00209. Make sure I got them in right, negative, positive, and those numbers look right. We go stats, calculators. Custom is the only one that's not in alphabetical order. Everything else on the calculators list is in order. Custom is doing its own thing. Values are gonna be your X and weights will be P of X. You gotta know where they're at. That's why I label them to make it easy to find them. Just click compute. And there you go, get your meeting that way. $7.50. Apparently, there's a very high standard deviation, but that makes sense when the outcomes are 530 and negative 249,000. All right, let's take a good 5-10 minute break or so. I'll stop the recording and do that as one video.